Drop a cup. Listen to the crash. Hear that single, final sound when something fragile meets the floor and shatters into a scatter of glass and memory. Now hold that image for a moment and ask yourself, could you honestly imagine the pieces slowly leaping back together? A film running in reverse, where glass reassembles itself and the cup floats gently into the hand that dropped it. The reaction is immediate, even instinctive. No, that won't happen. But why does our mind answer so fast? Why does nature seem to prefer one direction, from whole to broken, from ordered to scattered, as if then and now are separated by some built-in rule? Before we dig into the deep physics, try a quick little test in your head. Picture 3 different scenes: a wave rolling up a beach and crashing into foam, a drop of black ink hitting clear water and swirling until it dyes the whole beaker, and someone speaking in a room as the sound fades into silence. Now flip each of those scenes in your imagination and watch them run backwards. The wave would climb up the beach and knit itself back into a flat surface. The ink would compress into a tight kernel and leap out of the water, and the sound would gather from silence into a word. Something about the reversed versions feels absurd, even funny. We laugh when a movie of someone walking backward looks weird. We instinctively label one direction past and the other future. Our memory collects traces of what happened and not what will happen. This is the psychological asymmetry. We remember the past, not the future. We regret the past and plan for the future. In everyday life, then and now feel separated by an arrow that points from what was to what is. But suppose we take a closer lens, a physicist's lens, strip away the drama and look at the microscopic rules. The equations governing planets, billiard balls, molecules, Newton's laws, Maxwell's equations, the basic interactions governing atoms and nuclei, these are largely indifferent to a sign change in time. If you wrote down a collision between 2 billiard balls on a pool table and played the math backward, the backward sequence still obeys the same rules. Show a film of a planet orbiting the sun and run it in reverse. The planets still obey gravity. Orbits simply trace a path backward in time. Nothing in those equations screams one way. At the microscopic level they are, for the most part, time-symmetric. That's the puzzle. How can a universe built from time-symmetric laws give rise to a world where eggs don't unscramble, where rooms get messier instead of tidier, where memories accumulate in one temporal direction? If microphysics doesn't pick out a direction, where does our arrow of time come from? Before we go deeper, if you want to keep following that frontier, subscribe for more explorations into thermodynamics, cosmology, and the surprising ways simple principles give rise to the world we live in. Let's begin with the things that appear to have an internal direction: friction and complexity. Imagine sliding a wooden block across a tabletop. It moves for a while, then slows, then stops. Where did the kinetic energy go? Not to nowhere. It's been siphoned into microscopic motion. The block's surface atoms jitter, the table's molecules wiggle a little more, the surrounding air warms imperceptibly. Organized motion, the block gliding, turns into disorganized internal motion. Heat. That loss of organized motion to thermal jiggling is irreversible in practice. You don't see a block, warmed by the friction it experiences, spontaneously gather speed again and glide off. But the microscopic processes behind each collision, each interatomic interaction, are still reversible in principle. The apparent irreversibility of friction arises from complexity. An enormous number of microscopic degrees of freedom soak up the order. To see why complexity changes everything, let's zoom in from the block to the molecular level with a more vivid example. Fill a glass with clear water. Hold a dropper of black ink above it and let a single drop fall. The black ink flares, curls and spreads until the entire glass takes on a grayish tint. Now imagine reversing the movie. The grey water would suddenly pool black and then condense back into a single perfect drop and hop back into the pipette. The microscopic laws that govern each tiny molecule of ink and each water molecule don't forbid such a reversal. In principle, if every molecule retraced its path exactly, the water would separate itself again. But here's the catch. The number of microscopic arrangements that correspond to mixed dwarfs, those corresponding to separated. There's one neat way for ink to be concentrated as a drop, and an astronomically enormous number of ways for it to be smeared and mixed. Think of it like a deck of cards. A perfectly ordered deck is a special arrangement. Shuffle the deck once, and it's unlikely to return to that same pristine order. But now scale the deck up from 52 cards to Avogadro's number, about 1023 particles, and the space of possible shuffles explodes beyond imagination. The ink's mixed state corresponds to an enormous cloud of micro-configurations. The separated state is a tiny sliver. Random molecular collisions wander through the huge cloud and overwhelmingly remain within regions that look mixed on the macroscopic scale. To go back to the ordered tiny region is not forbidden by the rules, but it is vanishingly unlikely. In the language physicists use, the entropy, roughly the count of microscopic ways to realize a macroscopic description, increases because there are more microstates compatible with disorder than with order. There's a useful, almost childlike way to see this. Suppose the ink and water system has, for the sake of the thought experiment, 1,000,000 ways to be separated and 1,000,000,000,000 ways to be mixed. If you toss the system's microstate randomly, you have a tiny chance to land on a separated arrangement and a huge chance to land on a mixed one. When you start with a separated arrangement, that special drop of ink, and let the molecules randomly bump into each other, they are far more likely to wander into one of the 1,000,000,000,000 mixed configurations than to somehow come back to one of the 1,000,000 separated ones. It's a question of counting. Multiply that counting by the roughly 10^23 particles in a typical glass of water, and you quickly cross into territory so improbable that never in practice is a fair way to translate the numbers. And if this is helpful to you, let me know by liking this video. This feedback tells me this work is worth continuing. Now, let's try a slightly different device. Films played backward. Physicists sometimes do this as a mental exercise. Pick a short clip, a comet tracing an arc, or a planet revolving around the sun. Play it backward and ask whether the backward track still obeys the laws. For gravity, it does. If a planet moves along a precise orbit forward in time, it moves along a precise orbit backward as well. There's no law of gravity that tells the planet which time direction to take. The micro-laws say nothing about past or future. They talk about positions and velocities that can be reversed. So if fundamental interactions are indifferent to the direction of time, the asymmetry we see must be emerging from something else. Here's a telling thought. Take a film of a billiard game, where a shot breaks the rack and the balls spill across the table into a complicated pattern. If you run the film backward, the trajectories still look physically plausible. The balls collide and follow Newton's laws in the reverse direction. Yet if you examine a film of a cup shattering, the reversed footage looks implausible. Why the difference? Because in the billiard example, you can specify initial conditions, the precise positions and velocities of each ball, that lead to orderly motion, both forward and backward. Those initial conditions are special. In ordinary macroscopic events like a cup shattering, the initial microstate before the break is special. It is a carefully arranged micro-configuration that is extremely unlikely to occur spontaneously. Once chaos is unleashed, once the cup hits the floor, the microstate fissions into an enormous zone of possible configurations, almost all of which look broken at our macroscopic level. Randomness will push the system into that huge zone, and it won't return, except with absurdly tiny probability. This probabilistic perspective gives us an intimate friend with a disagreeable name: entropy. For clarity, when I say entropy in this conversation, I mean something operational. It is a measure of how many micro-configurations correspond to a macroscopic description. Higher entropy means more possible micro-arrangements. When ink mixes, entropy goes up because the number of compatible microstates swells. When your block slows down and its kinetic energy becomes heat, entropy goes up because the energy has been redistributed among many more microscopic degrees of freedom. Entropy is not a mystical measure of messiness alone. It's a counting measure, and counting is a very unromantic but accurate way to see why some transitions are overwhelmingly more likely than others. At this point you might already sense the answer to the cup question. Then and now are not separated by a change in the fundamental laws, but by the fact that the then, the early condition, was special and of low entropy. If the universe had always been in a typical high-entropy state, you would expect no direction, no reliable history, no consistent records, no memory. But our universe, crucially, began in a state that was far from typical. It started ordered. And that special initial condition biases the entire subsequent unfolding toward states of higher entropy. Before we get to cosmology, though, let me show you one more thought experiment that sharpens the intuition about usable energy and the importance of gradients. This one was deployed often to test ideas about extracting work from random motion: the ratchet. Picture a little wheel with asymmetric teeth, a ratchet wheel that can turn only one direction because of a pole that clicks into the teeth. Now suspend this wheel in a gas of molecules that jostle it, and imagine the pole is rigidly attached and helps the wheel step forward with each jostle. At first glance, this looks like a clever way to turn random thermal jiggling into directed rotation and thereby extract work from the thermal bath. If the gas molecules randomly impart pushes, why couldn't the ratchet harness these pushes into a steady rotation? That would be, in effect, a perpetual motion machine of the second kind, inventing usable work out of ambient thermal motion. Our physicist's nose twitches. Something is fishy. To see the problem, we have to notice one overlooked fact. The pole and wheel are themselves at the same temperature, subject to the same thermal jiggling. The pole wiggles. Sometimes it lifts at a moment that allows the wheel to slip backward. The very thermal motion we hope to harvest works just as easily to undo any biased motion. If the entire device, wheel, pole, axle, is in thermal equilibrium with the gas at the same temperature, the net rotation averages to zero. The ratchet cannot, at uniform temperature, extract useful work from random thermal motion. It's only when you introduce a temperature difference, when the pole is cold and the gas is hot, or vice versa, that a systematic bias arises and you can get net rotation. In thermodynamic language, you need a gradient, an availability of free energy, to do work. Heat alone, uniformly distributed, is not a free lunch. What this ratchet idea demonstrates is essential. Microscopic jiggling isn't automatically a source of useful directed motion. It can and does scramble order into disorder. That's entropy increasing. But turning that disorder back into order requires something extra. A difference, a priority, a gradient. In the housekeeping of the universe, gradients are what allow clocks to tick, engines to run, and us to do things. Without them, everything is stuck in equilibrium, where nothing useful can be extracted. So we've seen several things by now. Microscopic laws are largely time-symmetric. Macroscopic irreversibility arises because special initial conditions and vast numbers of particles make some macrostates astronomically more likely than others. Heat is the spread of organized motion into disorganized jiggling. And work, the currency of organized change, requires gradients. All of this fits together like an explanatory chain that runs from micro rules to our macroscopic experience of time's arrow. Still, something nags at us. Statistical reasoning explains why broken cups tend to stay broken given a starting point of low entropy, but it doesn't yet explain why that starting point existed at all. It just pushes the mystery back a step. If the present is biased toward higher entropy because the past was low in entropy, what set that initial low entropy condition? You can see why this is the hinge of the whole story. Without an answer, or at least without a plausible framework, to account for that initial order, the arrow of time remains an empirical fact that requires a boundary condition, a special beginning. We can think for a moment about an alternative that was floated historically. Ludwig Boltzmann, thinking about fluctuations in a vast thermal sea, suggested that low-entropy patches could arise by chance as fluctuations. In such a picture, even a tiny low-entropy pocket could occasionally appear in a mostly high-entropy universe, and within that pocket you'd find ordered phenomena like life. But there's a problem if we take that thought too literally. If fluctuations are the explanation, the most probable way to get a conscious observer is the smallest fluctuation necessary to create that observer entangled with a localized environment. The so-called Boltzmann brain problem. That predicts that orderly large-scale features like coherent cosmic microwave background patterns or galaxies that appear consistent everywhere would be exceedingly unlikely. Our observed universe is coherent across enormous scales. It looks like the result of a global low-entropy beginning, not a tiny random bubble. So while fluctuations are an interesting idea, they don't square easily with the breadth of cosmic order we actually see. Now pause and bring the cup back to the floor in your mind. The cup shatters because the micro-state before the drop was special. The subsequent motion explores an astronomical number of micro-configurations that make brokenness ubiquitous. The ratchet shows you that thermal motion alone, when it's uniform, cannot be funneled back into order without a gradient. The mixing experiment reveals how counting microstates makes some macrostates vastly more probable. The only piece left that we haven't fully opened is that initial condition, the fact that the early universe was in a low-entropy state. This is not some tiny detail. It is the hinge that makes the whole asymmetric spectacle we live in possible. At this point, you might be asking, is the asymmetry only in the state of the universe, or also in our minds? Why do we remember the past and not the future? Why do causes seem to precede effects in everyday explanations? The answer threads back through the statistical account. Memory is a physical record, a pattern etched into matter that correlates with prior events. Those records were written when the universe had available gradients and low entropy to spare. Writing a record is a process that increases overall entropy, even as it creates a local decrease in uncertainty for the observer. The directionality of writing records aligns with the global direction of increasing entropy that sprang from the low-entropy past. In short, our brains, our journals, and the fossils in rock layers all point in the same direction because they are consequences, records, of processes that ride the same statistical wave. That uneasy feeling, understanding the explanation, yet sensing that something still doesn't fully settle, is not an accident. I left something for that moment in the first pinned comment. It's for those who are done pretending surface answers are enough. We have now built a chain of understanding that takes us from the microphysical neutrality of the laws through the statistical weight of configurations to the macroscopic arrow we experience. Then and now are not separated by a new law of physics that forbids reversal. They are separated by improbable statistics grounded in the universe's initial condition. Nevertheless, we haven't yet reached the deepest question: why that particular initial condition? Why was the early universe so special? Before we open that door, let's linger a little more with the micro to macro logic, because it is wonderfully robust and because it answers many practical puzzles. Consider a simple act like mixing two gases by opening a partition between them. If the gases are identical, nothing dramatic happens. There is a diffusion toward uniformity. If the gases are different, say oxygen on one side and nitrogen on the other, when you remove the partition, they mix irreversibly. The microscopic collisions that redistribute molecules are symmetric in time, but the mixed state corresponds to vastly more micro-configurations. If you put a partition back in at some later time, you'll find that only one small fraction of microstates would restore the original segregation. You would have to fine-tune the positions and velocities of a mind-bogglingly large number of molecules to reverse the process. Practically speaking, there's no way to create that reversal except by contrivance. In experiments, physicists can and do arrange special microstates that run interesting backward evolutions, but these require careful preparation. They are the exceptions that prove the rule, highly controlled and non-generic. And that is why the cinema trick of reversing a planet film is so instructive. You can watch the reversed orbit and accept it, because the initial conditions were arranged to be compatible with both forward and backward narratives. When you see a reversed glass shattering film, you feel absurd, because the reversed trajectory would require an immense conspiracy of microstates converging at the precise moments needed to rebuild the cup. The improbability registers in us as impossibility, all of which leaves the ratchet thought experiment once more on the table as a practical test of whether microscopic fluctuations can do real, organized work. We saw that in thermal equilibrium, where everything shares the same temperature, the ratchet cannot produce a net rotation because the pole is subject to the same jitter as the wheel. But introducing a temperature gradient does allow for net motion. In the language of energy, gradients are the currency you spend to perform organized tasks. That is why heat engines run between hot and cold reservoirs. That is why life thrives where gradients exist. Across membranes, between sunlight and shade, between chemical potentials. Available energy, what thermodynamicists call free energy, is not mere existence of energy, but energy arranged so that it can be transformed into useful work. So you can see a picture forming. The macroscopic asymmetry we call the arrow of time comes from three ingredients woven together. First, time-symmetric micro-laws give the basic toolkit for dynamics. Second, statistical counting shows that starting from special low-entropy arrangements, evolution overwhelmingly heads toward higher entropy simply because there are more ways to be disordered. Third, the presence of gradients, disparities in temperature, pressure, chemical potential, provides the means to do organized work and leave records of the past. Together they produce a universe in which broken cups stay broken, ink mixes, and memories point backward. And yet the cosmic question lingers. What set the initial low entropy? It's an enormous question that touches cosmology, quantum gravity, and perhaps concepts we are only beginning to form. Some speculative ideas try to push the question back. Maybe an earlier phase produced the low entropy condition, or maybe cosmological inflation smeared and flattened certain features. Or perhaps the initial condition is a boundary statement we must accept as brute fact for the present-day physics to make sense. Each idea has its virtues and its problems, and none is yet a comfortable, settled answer. But before we step out into that broader terrain, I want to show you one subtle way the statistical argument reappears in another guise, in the reliability of historical knowledge. Take geology, for instance. A geologist reads rock strata and reconstructs a sequence of events. Rivers flowed, sediments settled, a mountain rose, erosion exposed deeper layers. These narratives work because records, layers, fossils, mineral alignments are feasible to form when gradients and low-entropy resources are available. The processes that write these records tend to be irreversible in the macroscopic sense because they move the system into overwhelmingly probable macrostates. The success of historical sciences rests on the same physics that forbids a cup from reassembling itself spontaneously. Records are asymmetric because the formation of records is a process that increases entropy globally while producing local, durable correlations with past events. We are getting close now to a hinge where multiple threads converge. We have dug from the floorboards of friction to the spinning of ratchets to the cosmic early hours where entropy must have been small. Each step is consistent and physically intelligible. The brain's assumption that then and now are separate, that the past is fixed and the future is open, is not magic or doctrinal ignorance. It is the sensible reading of a universe that began in one special way and evolved forward into a multitude of fates. And yet, there remains the open door. We can assemble the mechanics of the arrow of time with clarity and confidence, but the origin of the initial condition that makes all this possible is not an item on the same shelf. It is, instead, a question that asks us to look beyond statistical mechanics into the realm of cosmology and the origins of the cosmos itself. To understand whether that low-entropy beginning was inevitable, accidental, necessary, or a reflection of a deeper law, we must leave the comfortable room of object-level physics and step into speculation and observational cosmology. There are routes to explore. Scrutinize the cosmic microwave background for fingerprints. Examine inflationary scenarios for clues. Consider whether boundary conditions at the edge of space-time might be constrained by principles we have yet to discover. Before we go there, take a breath and return to the image that started us, the cup on the floor. It is more than an anecdote. It is a microcosm of a grand explanatory chain. The cup shatters, entropy increases, and our world moves toward states of higher multiplicity. Your mind treats then and now as different because the universe set up a direction to begin with. The microscopic laws are silent on direction. The macroscopic arrow is a consequence of counting and boundary conditions. We understand the mechanism, the statistical glue. We do not yet know the initial code, and if this is resonating with you, write this exact line in the comments. Entropy is the reason time feels one way. In the next stretch, we will push deeper. We will look squarely at the early universe, what cosmology tells us about its entropy, how fluctuations and inflationary ideas fit or falter, and why some tempting solutions, like the notion that our visible patch is just a random fluctuation in a larger chaotic bath, led to paradoxes that are hard to swallow. We'll also take another close look at the ratchet, the towel, and a few more thought experiments to make precise the distinction between energy that exists and energy that is available to do work. For now, keep the cup and the ink and the ratchet in your imagination as you prepare to follow the arrow back to its origin. We step now with steady feet toward the place where physics hands the question back to cosmology. We have a chain, reversible micro-laws, overwhelming statistics, gradients that allow work and record-making. That chain explains why cups stay broken and ink stays mixed. But the hinge of the chain is the special starting point, an early universe that was, in a precise sense, unexpectedly ordered. Let's examine what ordered meant for the cosmos, why that matters, and what the leading ideas and puzzles are when we try to push the arrow of time all the way back. Look first at the baby photograph of our universe, the cosmic microwave background, a faint afterglow from about 380,000 years after the Big Bang. It's almost uniform across the sky, with temperature variations of only a few parts in 100,000. That near uniformity is the image of extraordinary smoothness. If you imagine matter and radiation at that moment, they were distributed with a gentleness that is striking. From a thermodynamic viewpoint, that smoothness is not what you expect if gravity were already allowed to do its usual business of clumping matter into stars and galaxies. Under gravity, clumping usually increases the number of ways a system can be arranged. That is, it increases entropy. A smooth, uniformly spread mass distribution corresponds to a surprisingly small number of gravitational microconfigurations, which means low gravitational entropy. This is a subtle point, and it often trips people up because they conflate thermal entropy, random jiggling of molecules, with gravitational entropy. A hot gas spread evenly through a box has high thermal entropy in the sense that its molecules can be arranged in enormously many ways with the same gross description. But if you let gravity act, that evenly spread gas can lower its gravitational potential by clumping, releasing energy in the process, and creating many more gravitational microstates. So the early universe, while hot in the thermal sense, was extraordinarily low in the sense of gravitational entropy because it was so smooth. That low gravitational entropy is exactly what allowed structure, galaxies, stars, planets, life, to form later. If the early universe had been already clumped, stars and galaxies would have been different, and crucially, the entropy budget would look very different. Why does this matter for the arrow of time? Because entropy increase, and with it the direction in which records form and processes run, is relative to the initial low entropy condition. If the universe began with low gravitational entropy, the subsequent evolution toward clumping and complexity naturally produces a temporal asymmetry that cascades into every corner of experience. Heat engines run, chemical gradients are exploited, brains form memories, and history becomes readable in rocks and fossils. In short, the global low-entropy beginning sets the scoreboard. Everything that follows plays out as an account of growing multiplicity of microstates. Several ideas have been offered to explain how that early low-entropy state could arise. These ideas range from modest reinterpretations of boundary conditions to bold speculative frameworks that reach into quantum gravity and cosmology. Let me sketch a few of the better-known paths and, importantly, mark where they stop being established science and start being conjecture. One route that often appears in popular accounts is inflation. Inflationary theory suggests that a tiny patch of space underwent an enormous, accelerated expansion very early on, smoothing out any initial wrinkles and stretching quantum fluctuations into the seeds of later structure. Inflation explains several otherwise puzzling features, why the universe looks nearly flat and why distant regions have similar properties. But it is not, on its face, an explanation of low entropy. Smoothing by expansion can take a small region and make it look homogeneous, but you must still ask, why was that initial region in the peculiar state that inflation can amplify? In other words, inflation moves the question one step backward rather than eliminating it outright. Some cosmologists argue that certain inflationary scenarios do reduce the need for fine-tuning, while others point out that the conditions required for inflation themselves seem special. The debate continues, and the cautious view is this: inflation is powerful and likely played a role in shaping the observable universe, but it does not yet relieve us of the fundamental question of why the cosmos began in a state of such low gravitational entropy. Others have tried to reformulate the problem in terms of boundary conditions on space-time. Roger Penrose, for example, proposed that the initial singularity of the universe had to satisfy a special constraint, what he called the Weyl curvature hypothesis, so that the geometry was smooth in a way that set gravitational degrees of freedom to a minimal configuration. The idea here is that maybe the laws of physics allow many mathematically possible initial states, but that only those with extraordinarily low Weyl curvature lead to a universe like ours. Penrose's proposal is elegant, But at present, it's a speculative constraint on boundary conditions, an additional postulate rather than a derived necessity. There's also the idea that cosmology might have a two-sided time symmetry at a deeper level. Perhaps what we call the Big Bang is a branch point, with time's arrow pointing outward on both sides. In that picture, entropy is low at the branch and increases away in both temporal directions. It's an intriguing mental image, but it raises difficult questions about why observers like us find themselves on one side or the other, and whether such scenarios can be made compatible with observed cosmic asymmetries. Then there's the Boltzmann fluctuation idea I mentioned earlier, which is historically important but ultimately problematic when confronted with what we actually observe. The fluctuation idea imagines an effectively infinite system in thermal equilibrium where occasional random fluctuations produce locally low entropy pockets. If those pockets were how universes like ours arise, then statistically, the most probable low-entropy pocket that contains a conscious observer would be the smallest possible fluctuation required to produce that observer. Hence, the Boltzmann brain problem. We don't see a universe that looks like a minimal fluctuation. We see vast, coherent structure and a long cosmological history. That mismatch undermines the fluctuation hypothesis as an explanation for our observations. Those theoretical avenues give us a sense of the terrain, promising ideas, partial successes, and stubborn gaps. The important takeaway is that mainstream physics is comfortable describing how an initially low-entropy state evolves into a high-entropy future. It remains unsettled on whether that low-entropy starting point was a brute fact, a result of deeper principles, or a statistical outcome of a larger cosmological ensemble. This is not a failure of physics so much as an honest demarcation. Thermodynamics explains evolution from conditions. Cosmology asks about conditions themselves. Let's return from the heavens to the household and probe one more concrete example that binds the cosmic to the personal: memory. You remember your morning coffee because a chain of physical processes created and preserved correlations between earlier events and later states of your brain. When steam rose, when aroma reached your nose, when your eyes saw the cup, molecular and electrical processes wrote patterns into neurons. Writing those patterns increased entropy somewhere, a small local decrease in uncertainty for you at the expense of a larger global increase in entropy when you consider the energy consumed and the heat dissipated. In the absence of low-entropy resources, energy gradients to power neurons and metabolic machinery, you would not form memories. The directionality of remembering is therefore a physical consequence of the statistical and energetic conditions of the universe, not a metaphysical dictum. Memory is possible precisely because, going back in time, there was available free energy and a low-entropy past to bias the formation of durable records. This returns us to the psychological asymmetry. Our brains treat then and now as different, because the laws that write records work only in one macroscopic direction, consistent with the entropy gradient. If the universe had been in thermal equilibrium with no gradients, you couldn't get brains to write records at all. There'd be no reliable distinction between past and future to learn from. That's why, despite microphysics being indifferent to time's sign, cognitive processes are not. They are physical processes embedded in a universe with a direction imposed by its boundary conditions. We can, as an exercise, imagine what a world without that global asymmetry might look like. If the cosmos had been eternally at maximal entropy, or if entropy were stationary in time, then records and histories would be impossible. There would be no coherent past to reconstruct, and no accumulation of information. Physics as a science, relying on reproducible records and causally linked sequences, would not get off the ground. The very idea of science presupposes an asymmetry in which causes precede effects in the pragmatic sense, because records of causes persist. It is worth underlining one stubborn philosophical point. Statistical mechanics doesn't rewrite causality. It explains why, in a world governed by time-symmetric microscopic laws, but with an asymmetric boundary condition, causal narratives and the notion of past influencing future make practical sense. Causes are the low-entropy antecedents that, through overwhelmingly likely evolution, produce later effects and leave records. That's why geological strata, tree rings, and historical documents all point backward in time. Their formation processes are embedded in the same statistical bias stemming from the early universe. Before we conclude, let me offer one last thought experiment that is modest and tactile. Imagine you are on a beach, laying out two towels, one on a sunny rock and one in the shade. Over the day, the sunny towel dries faster because it sits in a region with a gradient. Solar energy evaporates water more efficiently there than in the shade. The towels are not violating thermodynamics when they dry. They are simply using an available gradient. Without the sun creating that local gradient, without the difference between sun-warmed air and shade, the towels would be stuck in a slower, less directional exchange, and you wouldn't gain much useful work from them. The towels are a small-scale analog of engines, memories, and organized structures. They all exploit differences to create order locally while increasing entropy overall. The universe's early low-entropy condition is, on the largest scale, the source of the gradients that let everything interesting happen. So what, finally, do we deliver to the title's claim? Richard Feynman explains why then and now aren't separate the way your brain assumes they are. The explanation unfolds in two clear sentences. First, the microscopic laws we use to describe particles and forces are largely indifferent to the arrow of time. That is, they are symmetric under time reversal in their essential form. Second, the reason the macroscopic world of cups, ink, towels and memories shows a direction is that the universe started in a very special state of low entropy. From that special beginning, overwhelmingly probable statistical evolution drives systems toward states with vastly more compatible microconfigurations. Thus, then and now are not separated by a new asymmetric law. They are separated by a boundary condition, the low entropy past, and by the statistical inevitability that flows from it. We end where we began, with a cup on the floor and the mental impossibility of watching it reconstruct itself in reverse. That feeling of impossibility is not an indictment of the laws of motion. It is an expression of probability and initial condition. To imagine the cup reassembling would be to imagine an extraordinarily conspiratorial coordination of microscopic states, possible in principle, but vanishingly improbable in practice. Your brain reads the imbalance between then and now because the universe's bookkeeping of microstates gave it reasons too. Records accumulate, gradients are consumed, and entropy tends to increase. And yet, there is a final, deliciously open question. Why did the universe begin with such low entropy? Was it a brute initial condition, a consequence of a deeper cosmological law, the result of a pre-Big Bang phase, or an outcome of a multiverse ensemble where patches like ours are the ones that can host observers? Physics has tools to make the consequences of a low-entropy start precise, and cosmology provides data that helps narrow theoretical options. But the why of the initial low entropy remains one of the deepest scientific questions we can pose. It sits at the crossroads of thermodynamics, quantum gravity, and philosophical reflection. If that combination of clarity and mystery has piqued your curiosity, there are good places to go next. Deeper dives into thermodynamics and statistical mechanics, lectures on cosmology and inflation, and accessible treatments of gravitational entropy and the Penrose hypothesis. If you want to pursue those threads in a guided way, there's a playlist of videos that unpack each step, from molecular collisions to the cosmic microwave background. For now, keep the image of the cup with you. It's small, immediate, and deeply revealing. The cup tells the physics story in miniature, micro-laws without direction, statistics that prefer the broken, and a past so special it carved an arrow through time. That is why your brain treats then and now as if they were different sorts of things, because the universe set up a temporal asymmetry at the beginning, and everything that follows reads like a consequence of that choice. We can explain the mechanics of the arrow. We cannot yet supply the ultimate motive behind the initial condition. And that, perhaps, is the best invitation science can offer. A clear map of what we know and an open, compelling frontier of what we don't. If you want to keep following that frontier, subscribe for more explorations into thermodynamics, cosmology, and the surprising ways simple principles give rise to the world we live in.